This is the second video for week number 11. So let's begin this video by looking at the following definition. Let A be a subset of R and let F be a function from A to R. We say that the function f has an absolute maximum on A if there exists some point x star in A such that f of x star is bigger or equal to f of x for all x in A. We say that f has an absolute minimum on A if there is some point x star down in A such that f of x star down is less or equal to f of x for all x in A. The point x star is called an absolute maximum point for f on A, while the point x star down is called an absolute minimum point for f on A. If these points exist, if these 2 points exist. Now, x star and x star down may or may not exist. So we are not saying that they always exist. Okay? Now let's look at what we call the maximum minimum theorem. Okay? It says if I is a close bounded interval, okay, say if I is a close interval AB and f is a continuous function on I, okay, then f has both the absolute maximum and absolute minimum on I. If I is a close bounded interval and f is a continuous function on I, then f has both an absolute maximum and an absolute minimum on I. So let's look at the proof, okay? Now, from the previous video, we know that if I is a close bounded interval and f is a continuous function on I, then f is bounded on I. Now, since we know that I is a close bounded interval and f is a continuous function on I, then the set f of I, okay, which is a collection of all points f of x such that x belongs to I, is a bounded subset of R. That's what we mean by saying that f is bounded on I. Okay, so you form a set whose elements are f of x where x is in I. You do that for all x in I, then you form a set which we call f of I, all right, and that set will be bounded, okay, by what we saw in the previous video. Okay, f is a continuous function on a close bounded interval, so f is bounded on I. Now, since f is bounded on I, that means f of I is bounded, and f of I being bounded means it's bounded above and below. Okay, so this set f of I is bounded above and below. Since it's bounded above and below, it means that both the supremum and the infimum exist. So let's denote the supremum of this set, the supremum of f of I by s star, and let's denote its infimum by s star down. Okay, now we want to show that there exists a point x star in I such that f of x star is equal to s star. Now, this is what we are saying. Now, since s star is a supremum of f of I, and every element in f of I is of the form f of x, where x is in I, then we have that f of x is less or equal to s star, f of x is less or equal to s star, all right, for all x in I, all right. Now, if we can show that there is an element, okay, x star in I, such that f of x star is equal to s star, right, then this will be f of x star, this will be f of x star, okay, that will be f of x star here, right? Then this will tell you that f of x, okay, is less or equal to f of star f of x star for all x in I, and therefore this will be an absolute maximum of f, absolute maximum of f on A. Okay, so that's what we are saying here. Okay, now since S star the supremum of f of I, all right, okay, and then for every natural number n, all right, S, this should be S star, okay, this should be S star, not S. Okay, since S star is equal to the supremum of f of I, then for every natural number n, S star minus 1 over n is not an upper bound of the set f of I, right? Because S star is a supremum, so if you subtract something positive, okay, what you get will no longer be an upper bound. So for each n, for each natural number n, S star minus 1 over n is not an upper bound of the set f of I, since S star is a supremum of f of I. And therefore, since this element S star minus 1 over n is not an upper bound of f of I, then that means there exists an element in f of I, okay, which is bigger than this number, S star minus 1 over n. But remember, elements in f of I are of the form f of x, such that x is in I, all right? So for us to say that there's an element in f of I, okay, which is bigger than this element here, right, means that there is an element in I, call it xn, right, such that f of xn, okay, is bigger than this number here, all right, okay. So what we are saying now is that since S star minus 1 over n is not an upper bound of f of I, then there is an element xn in I such that S star minus 1 over n is less than fxn, okay? But fxn is an element in f of I, right? And S star is the supremum of f of I. Therefore, f of xn is less or equal to S star, and that is true for all n in n. Okay, now since xn is in I and I is bounded, so let's assume that I is the interval, the closed interval from A to B. Okay, since xn belongs to I and I is bounded, then follow that the sequence xn is bounded. So that means each xn lies between A and B if we assume that I is the interval from A to B. Okay, and since xn is bounded, the Bolzano-Weierstrass theorem tells me that there exists a subsequence, call it xnk, okay, which converges. There exists a convergent subsequence, call it xnk. So let's assume that xnk converges to x star, right? Now, since xnk is a subsequence of xn, and xn belongs to I, then xnk also belongs to I, and therefore each xnk lies between A and B, since each xn lies between A and B, and xnk is a subsequence of xn. So this is true for all nk. And since this limit, if you take the limit of this sequence, you get x star. Take the limit, assume this is a constant sequence, this is a constant sequence, right? The limit here will be A, the limit here will be B, the limit here will be x star. So you end up with the fact that x star lies between A and B, right? So we are assuming that the interval I is the closed interval AB, so that tells you that x star belongs to the interval I, and therefore since f is continuous on I, then particular f is continuous at x star, right? Since f is continuous and and x and k converges to x star, okay, since f is continuous and x and k converges to x star, it follows that f, x, and k converges to f, x star, right? That's the limit as k goes to infinity, f, x, and k is equal to f of x star, all right? Now, from this one here, from this inequality here, right? X star minus 1 over n is less than fx and k is less than s, less or equal to s star. You have that s star minus 1 over nk, right, is less or equal to fx and k, right? And this is, sorry, strictly less. You have that s star minus 1 over nk is less than fx and k, and that is less or equal to s star. All right, that's what we get. And it's less or equal to s star. So now you simply apply the Squid theorem. You simply apply the Squid theorem here. You simply apply the Squid theorem here, okay? The limit here, you know, this will go to 0, okay, as k goes to infinity. So the limit here will be s star. The limit here will be f of x star, which is this one here, okay? And the limit here will be s star, okay? So you have that s star is less than f of x star, and this is less than s star, okay? So you have here s star, here you have fx star, here you have s star. So you have s star is less than or equal to this, all right? And you have this is less or equal to s star. So then the Squid theorem simply tells you the Squid theorem simply tells you that the limit as k goes to infinity of fx and k, right? Fx and k is equal to, which is equal to fx star, will be equal to s star, and s star is the supremum of f of I. Okay, so what we have obtained is that f of x star, right, is equal to s star, and that's what we wanted to get. Now, you can apply this a similar proof, okay, to show that the absolute minimum also exists. What you do in that case, you have to show that there exists an element x star down such that f of x star down is bigger or equal to f of x for all x in A. So you show that there exists an element x star down in I such that f of x star down is bigger or is less. Let me say that again. You have to show that there exists an element x star down in I such that f of x star down is less or equal to f of x for all x in A. The proof is just similar to what we have done here, and so I'll not go through it. Okay, so we have simply applied the Squid theorem here. Okay, you let x and k go to infinity. You let k go to infinity, and this will go to s star. This will go to s star. So you have that s star is less or equal to f x star, and this is less or equal to s star. Then you conclude that f of x star must be equal to s star.